So my name is Mauni, and I'm the architect for the .NET Garbage Collector. Today, I wanted to chat about techniques to diagnose memory leaks. So in this talk, I use memory leaks to mean only managed memory leaks. Of course, you could have native memory usage in your process, and how to diagnose those leaks are not in this talk. It's out of scope for this talk. The reason why I think it's useful to talk about this topic is that I often see folks take, a memory dump when they're attempting to debug a memory leak issue without considering the timing when they do that relative to when GCs happen. And that consideration really matters. In fact, it's very important. Yet I don't see that talked about often. So I'm going to first explain why I'm telling you that it matters. And then hopefully it'll make it obvious which techniques you should choose. So, all right. So first of all, what is a managed memory leak? In my mem document, this is a document that I wrote and maintain on GitHub that I have a link here. If you haven't read it, I would strongly encourage you to go find, sort of relevant sections that are of interest to you. But if you read the definition of a managed memory leak, it's a pretty long definition, right? And I'm not sure that everybody is familiar with the terms I'm using here. So I also put a link to user root, what that means. That really just means your code. Your code includes the code that you wrote and the code that you use in the libraries that you call. So a managed memory leak means you're leaking the kind of memory that GC cannot reclaim because you're holding it live, right? So GC, obviously has its own heuristics when to do a GC. And a lot of people have asked the question that I think I'm not holding on to this object anymore. Why isn't GC reclaiming it? Of course, GC is not going to do a GC as soon as an object is no longer held live by the user code, right? That would be incredibly inefficient. So GC will happen at some interval, and I will explain what those intervals are defined, how they're defined. So if you have a memory leak, even if we did, a full block in GC, which is the most extensive GC that we do, the heap size still ends up growing. I say heap size here, but it's actually not completely accurate, and we'll see why. All right, so now we got that defined. Oops. I want to talk a little bit about actually measuring memory usage in an environment with a garbage collector. So the memory area has a lot of confusing terms. You probably heard some of these, committed memory, reserved memory, etc. And tools often aren't consistent with the terminology, which makes it even more confusing. So I have a section in the mem doc that explains the virtual memory fundamentals. If you're interested in some of the low-level stuff, like how the hardware, how the OS works relative to how we work on our layer, I have a talk that I specifically did actually for our learning day last year that I shared on YouTube. So feel free to go watch it there. So what do you need to care about when you measure memory, right? If you want to debug memory leaks, that is. Most of the time, I would say you want to care about committed. Committed is the amount of physical storage that's used to actually store your data, right? Before you commit memory, you cannot write, in other words, you cannot store data into that memory. Most of the time, this correlates with working set, but it may or may not. I know that a lot of folks, they do measure working set, and working set is harder to reason about because working set means you are consuming this memory, but you don't know whether the OS kept it in the physical memory or not. So committed is a lot more easily correlatable to the memory, the memory you think you're using in your app. So most of the time, I would go with committed. So when to measure, right? as I mentioned, I often see folks just go to their server and take a memory dump at some point, right? It's they don't really ask like, when should I be measuring? So if you're not asking this question, you really should. Because if you think about it, if you're measuring, if you happen to measure on entry of a GC, that's when the heap size is at its largest for this GC, right? Because GC's job is to reclaim memory. And then if you happen to measure on exit of a GC, that's when the heap size is at the smallest during this GC. And if you think about, you happen to have a GC, that compacts the whole heap, then if you measure on entry and exit of that GC, you could see quite a big difference, right? So when do you want to measure? And just want to clarify that heap size means that the memory range on the heap that is actually occupied by objects. So we don't actually decommit space that we know we'll be using right away because that would be inefficient, right? So you would observe that you have some extra memory committed depending on where you are, relative to GCs. So I'm going to walk you through a sequence of what things might look like on a heap to illustrate this further. So when we start, right, you load up the runtime, you start allocating in your code. Your code, again, means the code that you wrote plus the code that you're using from libraries that you call. So, as you allocate, we commit as needed on this, what we call a heap segment. So right now, the committed is here. And then as you allocate more, we commit more, right? And then when you have, oops, I think, right, sorry. So I should have separated this slide into multiple, but what I meant to say with this slide is when a GC happens after you've allocated enough, right? So this is our first GC and it reclaimed memory from the last slide. So it reclaimed a bunch of memory and because it compacted. And if we decommitted all the extra space, it looks like this, right? Because the, I don't know if you can actually, yeah. So if we reclaim, so let's say, the objects used to go here and then we compacted, so we got rid of all this memory. And if we decommitted all that memory right away, it would look like this, right? So we committed would be here. And then we know that what would happen is you would allocate right away in here in this space, right? So that seems inefficient, right? If we know that we're going to be allocating in this space, which means we have to have the memory committed, right? You can't write data to it if you don't have it committed. Then we might as well just keep this space committed, right? So what actually happens is that we don't decommit that extra space right after GC, right? We have this other data, or this other field in our data structure that keeps information about the segment called allocated. So allocated, this is where the last object ends at the end of that GC, right? So we keep this space committed because we know you're going to be allocating in this space right away. And one of the frequently asked questions I get is, how come my heap size is quite a bit smaller than the memory usage of the process? Assuming when we say memory usage of the process, we actually mean the committed of the GC heap, right? Because if you have native memory usage, then that's not counted for the committed right here. So you could imagine that if you happen to look at your heap, like with SOS or some other tool, and you look at the heap size at this point, it would give you up until allocated, right? But if you look at committed for your heap, it will give you this value. So yes, like there can be quite a bit difference here. The space that we leave after allocated until committed for the segment is actually what we call the Gen 0 allocation budget. So I think some of you might have heard about this concept called an allocation budget. So recall that, a couple of slides ago, I said, after you've allocated enough, right? So what is enough? Enough means you actually exceeded the number that we set that we call the allocation budget for Gen 0. By the way, I'm talking about small object heap here. We'll leave large object heap out of this talk because it's not really relevant to illustrate the points. So you can see that what happens here is that if allocated is here after AGC, then when we resume the user threads, then you know that you'll be allocating here, right? And that is your allocation budget. And after you've exceeded this allocation budget, then we repeat the cycle, then another GC would be triggered. So if you think about server GCKs, which I imagine, many folks in, within the company working on server GC apps know that server GC actually has could have many heaps, depending on like how many processors you have and how many heaps that you specify, right? So if this is actually, not a small number, which it may not be, and you have that many heaps, it would be multiplied. So then if you happen to measure the heap size right after GC and the committed of the whole heap, you could see a lot of difference, right? So that's why you could see that discrepancy that people usually are, confused about. But now we get to the generation aspect, right? Because the .NET GC is a generational GC. It has 3 generations that I'm pretty sure that most of you are familiar with. Logically, we have 3 generations, right? We just have Gen 0, 1, and 2. So when you say like, I'm doing a GC of this generation, it never exceeds Gen 2, right? Gen 2 means you're collecting the whole heap. But physically, if you look at the GC code, which some folks are very interested to just, curious to look at, they will notice that we use Gen 3 and Gen 4 to denote the user old heap portion of the heap. So user old heap includes a large object heap and pinned object heap. Pinned object heap was added in .NET 5. So that's our new generation, Gen 4. However, this part of the heap is all collected with Gen 2 GCs. Right. So GC would choose to do either Gen 0, 1, or 2 GCs. And, Gen 2 collects the whole heap. So they're also called full GCs. So what doesn't get collected will act as what I call the internal routes to the portion that is getting collected, right? Because let's say you're doing a Gen 0 GC, which means you're not collecting what logically is considered Gen 1 and Gen 2 part. And Gen 2 includes Gen 3 and Gen 4, right? So whatever that you're not collecting means that, by definition, that portion of the, objects in that portion of the memory are considered live. So whatever they point to will need to be live as well. So they act as internal routes. And then when you're actually doing a full GC, these internal routes no longer exist because, well, you don't have any portion that you're not collecting. Okay. So because I mentioned that we want to measure the committed size, let's see an illustration of the heap when we're doing various kinds of GCs. Various kinds means, different generations. And when you do a full GC, you also have the option to do either a blocking GC or a background GC. So we'll see how that plays out. So this is where we have a Gen 0 GC happening. This is the beginning of a Gen 0 GC and the end. So notice that there's really no difference in committed there because of the reason I just mentioned, that we don't decommit the part that even though they no longer have valid objects occupying it, we know that you'll be allocating this space right away. So committed really doesn't change much. And then, you have another Gen 0 GC happening. Committed still just doesn't change much at all. And then now I have a Gen 1 GC happening, right? Because now Gen 1's allocation budget is exceeded. So how does Gen 1 allocation budget get consumed? Well, when you do a Gen 0 GC, right, whatever that survived from the Gen 0 portion of the heap, they need to go somewhere. So now they're considered part of Gen 1. And when they're, this is what we call promoting into Gen 1. When you promote into a generation, you consume that generation's allocation budget. So at some point, a Gen 1 GC happens. And this is the picture on entry of that GC. And then this is a picture on exit. So yeah, committed is retreated back a little bit, but not by much. Right now, if we have a Gen 2 GC happening, let's say this is a full block in Gen 2 GC that did compaction, right? So then you can see a very dramatic difference between the committed on entry and on exit of this GC, right? So yes, we're still keeping that Gen 0 allocation budget portion committed right here, but the whole heap, because it got compacted so much that the committed for the segment still got pushed back, to the lower address range a lot more. So then I mentioned that if you're doing a Gen 2 GC or a full GC, you have the option to do it either in the stop the world, which is the block in GC, or the concurrent fashion. Concurrent is what we call a background GC. And one thing to keep in mind about, excuse me, background GC is they do not compact. So the heap size actually doesn't change much. And background GC's job is it'll build up these free lists in Gen 2. So it'll accommodate survivors from Gen 1 GCs, right? So that's why you'll see that, okay, the heap size doesn't move much, but what we call the fragmentation is the sum of the items on the free list. It would increase potentially by a lot at the end of the background GC. So now if we look at the same picture before background GC, so this is the begin of background GC entry. We have this committed, right? And then, you'll see that committed doesn't really change much. However, if you look at the heap right now, it'll have some free items in, then we thread these onto the free list for Gen 2. I mean, of course, you could have free lists, you could have a free list in Gen 2 as well before you started this background GC, but they would occupy less space. Right. So after we talk about different generations, I want to quickly mention how we decide which generation to collect. So of course, the most significant factor is what we just talked about as the allocation budget. So if a generation's allocation budget gets exceeded, it means we would do at least that generation of collection, right? We have other factors. For example, when the physical memory load is very high. So how do we define the physical memory load? So I have a link to MemDoc that explains exactly what we mean by physical memory load. But you could just think of it as, how much of the percentage of physical memory that is occupied on the machine. Of course, if you're in a container, we calculate a value that's equivalent to that. So if it's greater or equal to 90%, it means it's very likely a Gen 2 compacting GC might happen, right? A block-in GC that does compaction. So of course that could get expensive, right? The pause could get long. So you'll likely see if you're not under memory pressure, meaning that if your physical memory load isn't high, then you get ephemeral GCs, which means Gen 0 and Gen 1 GCs and background GCs if we need to do a Gen 2 GC. And of course, if we only do Gen 2 GCs, if we only do background GCs for Gen 2, you could see a significant amount of fragmentation in Gen 2, especially at the end of a background GC, right? If you're under memory pressure, meaning the memory load is high enough, then you'll likely get full compacting GCs, right? And the pauses could be long there. So now we're coming back to the main topic of this talk, which is how do you conclude that you have a memory leak, right? Because this is actually not, I find that the way that folks determine whether they have a memory leak or not sometimes isn't actually the case that, they do have a memory leak. So I want to introduce a concept called the live data size, the LDS. So if the live data size is increasing, it means there is indeed a leak. The live data size means the part of memory that GC cannot possibly get rid of because it's held live by your code, right? So as we saw like a couple of slides ago, we have these things called internal rules when you're not doing a full GC, right? Because if we choose not do a full GC, then that part of the memory could contain objects that aren't held live by your code, but because we're not collecting that part of the memory, we'll keep it live, right? By the virtue of not collecting that generation. So only when you look at Gen 2 GCs and what survives from those GCs would you actually know what your LDS is, right? That's a part that cannot be gotten rid of if we, because you're holding it live. So of course, as we mentioned, that if you're doing a background GC, you could have fermentation on the heap, and LDS in that case means total GC, total heap size minus fermentation. In other words, the space occupied by your objects. Or another way to look at it is promoted bias, right? Because that's what actually survive after you do a full collection on the heap. So another thing that folks, especially if you work on server apps, that you probably are very familiar with is pinning, right? Pinning is especially prevalent if you have some sort of I/O. This could be network I/O or file I/O if you work on client apps. So one thing I always sort of suggest to folks is when they pin, they should have a good reason, because pinning really introduces a lot of stress on the GC. I'm only talking about the results of what you see on the heap after pinning is handled. But when GC has to handle pinning, that's actually a lot of work, right? It's much harder for GC to handle than if there wasn't pinning. But the end result is, if you have pinning, even if we did the expensive type of GC, the full compacting GCs, you still have fermentation on the heap because you have objects that we cannot move, right? So if you keep introducing new pins, of course, GC tries very hard to not let the pins stretch out the heap. But that's an effort, right? If the code insists on having more and more pins, you could see the heap size getting larger and larger, even with doing the full compacting GCs. So that's something that I specifically talk about in MemDoc. Usually these are due to pinned handles. So I talk, one of the sections I talk about how you would go about diagnosing those with Purview. I have a slide. So I'm actually not going to go through the slide, but I wanted to put it there because I think you could follow this yourself after the talk. So this illustrates what the heap, how the heap would be handled when you have pins, when we're doing compacting GC and we're not doing compacting GC, which we would call a sweeping GC, right? That's what background GC is. So that's sort of the background of what a memory leak is and how do you conclude that you have one. And now we're coming to the diagnosing part, right? So when the problem is simple, meaning that it's very easy to repro. You run your app or you run your test, you just see that, okay, my memory usage is getting larger and larger. Even when I'm running into memory load, high memory load situation, which means GC is trying very hard to compact the heap down, you still cannot get your heap smaller, right? That means you clearly have a managed memory leak problem, and the overhead of profiling is basically irrelevant because let's say you're in a test environment, you could even afford to put like a gc.collect after some iterations of a loop, then you'll just easily conclude that you have a memory leak and you can take a dump, right? People, usually the common approach is that they take a process dump. And if they're doing this on a server, when taking a process dump is allowed, they could take one and take another one after some time. They just compare the heaps. You could do this with the old way of doing this is with SOS, right? I'm sure many of you have used SOS. But my point is, when the problem is simple, pretty much any tool would do. I'm sure there's a bunch of third-party profiling tools that can easily give you the analysis of the heap. I'm talking about when you don't have that luxury, right? You can't just say like, oh, I'll just take a process dump or I'll just induce a full block in GC. So what are the techniques that we could use? Well, we have these counters, right? They're very lightweight and they can be collected and on all the time. So I'm sure some of you are familiar with the total committed bytes perf counter from .NET Framework. And in .NET 6, we added a .NET counter called committed bytes, right? So when we're adding this counter, I had a discussion with our diagnostics team whether we should add both the committed bytes on entry of the GC and on exit of the GC, or just one of them, right? So by the way, the number of total committed bytes from .NET Framework, that's after GC. Like most counters that we have, their values on exit of the GC. So our conclusion was you will keep that policy. We'll give you the end of the GC committed bytes. So then the question is, then how do I know the beginning of the GC? But as we have seen, unless you're actually doing one of those very expensive GCs, your committed bytes actually doesn't change all that much. So let's say you have just done a Gen 2 block, compacting GC, and committed bytes went down by a lot. But keep in mind that the committed bytes you get from the GC prior to this would be basically what you got when you're on entry of this expensive GC, right? So you still get the full view of the data. So then we kept it at one counter that's the end of the GC to be consistent with the .NET Framework version. So if you read any of the blogs I wrote, that my favorite tool to diagnose performance problems is Purview, right? I'm sure other tools could do similar things, or at least some of the things that Purview can do. Not all of them. Some of the things I've discovered, only Purview has such functionality. But the things I'm describing in this slide, I believe that Purview is not the one that can do it. How do you collect the top level GC events so you can check out the promoted bytes for Gen 2 GCs? That's something that I believe other tools can do as well. And I have a link to tell you how to collect the top level GC events that's documented in memdoc. This is something that you could do on production because it's very, very lightweight. Some people, they already have the mechanism to collect ETW events or just events, right? If you're on Linux, you can go with the event pipe events, which is a built-in mechanism in the runtime. So you could collect the top level GC events, and that's enough to show you the promoted bytes for each GC that we've done. So if you look at promoted bytes for Gen 2 GC, you can figure out, like, do I have a memory leak or not? So I have an example here. This is just from actually a trace the customer sent me. So I am listing all the, or some of the 2B means background GC, right? It's Gen 2 and background. So as you can see, if I look at the promoted byte or megabyte column, they're roughly the same. And then the peak and after are, the peak is noticeably larger than after, but after still got quite a bit of fragmentation, as I mentioned, that's background GC's job, then promoted, right? But in this case, we can conclude that we don't have a managed memory leak. But one of the questions that are not exactly related to diagnosing memory leak, but something that I've gotten asked quite often lately is, what if I don't want as much fragmentation when I'm only doing background GCs, right? So we actually added a new config called GC conserve memory. So you could specify integer value 1 through 9 inclusive. That tells the GC how conservative you want it to be when it comes to memory usage. So this means that the higher value that you specify for this config, the more conservative GC would be when it comes to taking up space, right? So if you specify, let's say 9, that's when GC is most aggressive at reclaiming memory, which means it might start doing some full blocking GCs just so that we can compact the heap down, right? If you specify very low value, then GC isn't as aggressive. So then the question is, well, you're telling me that if my app grows very large, that I would hit the high memory load situation, and GC would do a very, like a full compacting GC anyway, which would likely shrink my heap size, right? Unless you have pinning, when GC, you can't really do much about that. So why would I want to specify this conserve memory config, right? Well, I find this is mostly good for capacity planning, which means, like, if I can sort of make it predictable or more predictable how much memory my app can comfortably run in, right, by using this config. So I know, like, okay, like my app can comfortably run in with the conserved memory of, let's say, value 5. So it doesn't grow so much until, it only gets compacted down when I hit the memory load, high memory load. So that makes it easier to plan out, like how many processes can I put on each box, right? And you know that if you have a condition that makes, let's say like some processes use more memory than expected, but when they use enough that you hit the high memory load situation anyway, you will get full compacting GCs, compact them down instead of getting out of memory exception. And it's good to use purview to collect, GC events or some other way to collect GC events. But what if I want to do this in-proc, right? Folks have asked like, oh, but I have a bunch of, diagnostics code in-proc, and it would do something with the process when I detect in real time or near real time something's happening, right? So in .NET 5, we introduced a new API, which is actually a new version of this get GC memory info API that I introduced in .NET 3. So when I introduced this original API in .NET 3, it was really just meant for being used by some library code. So it only included info that library code needed. So it was fairly minimum. But in .NET 5, we got clearly feedback from folks that they wanted more and richer info about each GC. So well, I mean, this provides a lot more than what I'm listing here, but I'm listing the relevant information that's to our topic, which is that you can get memory info on specific kind of GCs, right? Let's say you really only care about like Gen 2 GCs because you just want to detect when you have memory leaks. That means that you want to get GC memory info on these two kinds of GCs, either background or full blocking. And then you want to see, essentially see the equivalent of that promoted bytes or promoted megabytes in purview, right? That column I just showed. So you would calculate that by looking at the generation info, which gives you the size after bytes. Size after means on exit of this GC, and fragmentation after bytes, which means the fragmentation I observe on exit of this GC. So I have a little code snippet that would calculate this LDS for you. You could imagine putting this code maybe on a thread that does the periodical monitoring, and then when you detect that LDS is larger than what you expected, you take some action in the process. So let's say we concluded that we do have a memory leak, right? So how do we know what objects are there on the heap, that these are the objects that GC cannot get rid of? So purview allows you to collect a heap snapshot in a not so intrusive way, right? So if you open up this take heap snapshot menu in purview, you'll see like there's this freeze option, which you can uncheck, which tells purview that don't pause all my threads in order to take this heap snapshot. Just do the best job you can, right? Because of course, while your thread's running, purview will go take a snapshot opportunistically. And if you have already captured a process dump, right, which is a kind of a common practice for a lot of people, that you can also load that into purview, which would show you the object types, how many of them there are, and the connectivity among them. And in .NET 5, we also introduced this new generation aware diagnostic that I'm not aware any other tool does. So this is, I've gotten comments from folks when I talk about this analysis in other talks. They're like, oh no, I have tools that gives me the generations of the GC. I know how big my Gen 0 is, Gen 1 is, or Gen 2. So this is very different from that. This generation aware does not mean I'm able to look at different generations of a heap. This means I want to do my analysis. One is doing a GC of this generation, right? So this was actually added mostly for debugging ephemeral GC problems. So you'll observe that, oh, my ephemeral GCs usually have pretty short pause, but occasionally I see these long pauses and I see a spike in the promoted bytes, right? So which means like, oh, normally I would promote, let's say, you know, half a meg, right? But suddenly I see that promoted MB column jump to like 3 megs. Then naturally, you know, GC would take longer. So this was actually added for that purpose because I haven't really observed any other tool that would give you this kind of option. So what you're telling the runtime to do is I'm going to tell you the generation of the GC that I'm interested in analyzing. And I'm going to tell you the minimum survived bytes or promoted bytes, right? They're interchangeable, observed in this GC. And I'll give you a min GC index, right? So of course, this is all observable from the top level GC bands. So the third option that you specify, the min GC index, this is to avoid certain phases. So you'll observe that in the startup phase, right? Some apps may have multiple startup phases, but startup phase really just means like this is when you're allocating a bunch of static objects that will likely live until, you know, either very long or until the end of the process. So by definition, lots of stuff that you allocate will survive, right? And that's desirable. And of course, so in that case, if you look at especially ephemeral GCs whose survival rate is usually low because they're for, you know, very temporary objects, at this point, their survival rate by definition would be high because most things from those generations would survive, right? So you want to avoid that and you want to give it the GC min GC index to get past that part. So then you could say like, oh, you know, I observed that, you know, usually it's half a meg, but I want GC to capture a trace that shows me the connectivity of objects and their types. When I observe a GC that's at least with this index and with, I think I said 3 megs survived bytes, right? So what we do in the runtime is when you specify these, you know, it's specified by environment variables. When we detect such a GC, we would capture an ETW trace or a trace. I should stop saying ETW because, you know, some folks are on Linux. And then we would capture a trace that would show you the info that you can then open up in Purview to look at the object types, size, and connectivity. You could, of course, then we discover like, oh, this is actually quite useful for debugging memory leaks because you could tell it, you know, I'm interested in Gen 2 GCs. And by the way, you know, if I'm already in the situation where I'm seeing some full blocking GCs, right, the Gen 2, especially the compacting GCs, and the heap size is not getting compacted, I would like to know why. This is especially useful when you have unpredictable situations. As in that, you know, on most of my production machines, I observe that I'm only using the expected amount of memory when I'm hitting these, you know, full blocking GCs. But on maybe a small percentage of my machines, I'm observing that I'm getting out of memory exceptions, right? So you could use this and it would, you know, it introduces a very low overhead if such situation doesn't happen. But if we do see that, oh, on this machine, I'm observing that I'm surpassing the minimum survived bytes that I specified, then it would take a trace then. So these are environment variables that you set. And my example says that, you know, if I'm doing a full block in GC, because this analysis is only active for block in GCs, and if it survives at least 1 gigabytes and GC index is at least 1,000, so these are all hex numbers, then capture a trace. But we discovered that, you know, when we capture a trace, sometimes that's not as nice as a dump because dumps would show you more information. So in .NET 6, we added an option to capture a dump. And I have a link here that's from my teammates who wrote a blog entry on the generation aware analysis. You know, he's the one who implemented this. So I wanted to talk about one of the other frequently asked questions that I get asked perhaps once a few times every year since I started working on the GC. So I have a very simple program here. So I allocate a new object and I allocate a weak handle to it, which means I'm saying that my handle is not going to keep this object alive. And then I don't use this object anymore, right? Not after this line actually. And then I do a GC collect, right? As I mentioned, when you're doing it, so this introduces induces a full collection. That's blocking, right? This is like one of the older overloads for this collect APIs. So I'm saying that, just GC just collect whatever that my user code isn't holding on to. And I know at this point, my user code is not holding on to O anymore. At least I think so, right? But when we do this target check, we see that it's not actually collected. So I get asked, like, why isn't GC collecting my object? I already let it go. You said whatever that I'm not holding on to, if I'm doing a full block in GC, it should all be gone, but it's not gone. It turned out that, well, JIT is free to lengthen the lifetime until the end of the scope, right? So here's the end of the scope. And it's perfectly legal for JIT. And this behavior has been there since the beginning of .NET Framework 1.0. That JIT is free to lengthen the the lifetime of object O until the right here. So that's why in this case it's not actually collected. And by the way, you cannot rely on this because in one version, JIT could decide like I'm going to lengthen your object lifetime, but in the next version it might not. So the way to make absolutely sure to let JIT not do that is you put this in a different scope and you disable inlining. So in this case, you'll see that it is collected. So that's the way that, especially in these like very, very micro benchmarks, a question that I often get asked that I thought I'd clarify when I get an opportunity so folks are not confused by it. So that's all I wanted to cover today about memory leak diagnostics.